on D2 with D2 and current slope. Hello, my name is Andre, and I've been training deep neural networks for a bit more than a decade. And in this lecture, I'd like to show you what neural network training looks like under the hood. So in particular, we're going to start with a blank Jupyter notebook, and by the end of this lecture, we will define and train a neural net in everything that goes on under the hood and exactly sort of how that works in the intuitive level. Now, specifically, what I would like to do is I would like to take you through the building of micrograph. Now, micrograph is this library that I released on GitHub about 2 years ago, but at the time I only uploaded the source code, and you have to go in by yourself and really figure out how it works. So in this lecture, I will take you through it step by step and kind of collect all the pieces of it. So what's micrograph and why is it interesting? Micrograph is basically an autograph engine. Autograph is short for automatic gradient. And really what it does is it implements backpropagation. Backpropagation is this algorithm that allows you to efficiently evaluate. Interesting. Micrograph is basically an autograph engine. Autograph backpropagation. Backpropagation is this algorithm that allows you to efficiently evaluate the gradient of some kind of a loss function with respect to the weights of a neural network. And what that allows us to do then is we can iteratively tune the weights of that neural network to minimize the loss function and therefore improve the accuracy of the network. So backpropagation would be at the mathematical core of any modern deep neural network library, like say PyTorch or JAX. So the functionality of micrograph is, I think, best illustrated by an example. So if we just scroll down here, you'll see that micrograph basically allows you to build out mathematical expressions. And here what we are doing is we have an expression that we're building out where you have two inputs, A and B. And you'll see that A and B are -4 and 2, but we are wrapping those values into this value object that we are going to build out as part of micrograph. So this value object will wrap the numbers themselves, and then we are going to build out a mathematical expression here where A and B are transformed into C, D, and eventually E, F, and G. And I'm showing some of the functionality of micrograph and the operations that it supports. So you can add two value objects, you can multiply them, you can raise them to a constant power, you can offset by 1, negate, squash at 0, square, divide by constant, divide by it, etc. And so we're building up an expression graph with these two inputs A and B, and we're creating an output value of G. And micrograph will, in the background, build out this entire mathematical expression. So it will, for example, know that C is also a value. C was a result of an addition operation, and the child nodes of C are A and B, because it will maintain pointers to A and B value objects. So we basically know exactly how all of this is laid out. And then not only can we do what we call the forward pass, when we actually look at the value of G, of course, that's pretty straightforward. We will access that using the .data attribute. And so the output of the forward pass, the value of G, is 24.7, it turns out. But the big deal is that we can also take this G value object and we can call that backward. And this will basically initialize backpropagation at the node G. And what backpropagation is going to do is it's going to start at G, and it's going to go backwards through that expression graph, and it's going to recursively apply the chain rule from calculus. And what that allows us to do then is we're going to evaluate basically the derivative of G with respect to all the internal nodes, like E, D, and C, but also with respect to the inputs, A and B. And then we can actually query this derivative of G with respect to A, for example, that's A.grad. In this case, it happens to be 138. And the derivative of G with respect to B, which also happens to be here, 645. And this derivative, we'll see soon, is very important information because it's telling us how A and B are affecting G through this mathematical expression. So in particular, A.grad is 138. So if we slightly nudge A and make it slightly larger, 138 is telling us that G will grow, and the slope of that growth is going to be 138. And the slope of growth of B is going to be 645. 138 is telling us that G will grow, and the slope of that growth is going to be 138. And the slope of growth of B is going to be 645. So that's what it tells us about how G will respond if A and B a tiny amount in a positive direction. Okay. Now, you might be confused about what this expression is that we built out here. And this expression, by the way, is completely meaningless. I just made it up. I'm just flexing about the kinds of operations that are supported by micrograd. What we actually really care about are neural networks. But it turns out that neural networks are just mathematical expressions, just like this one, but actually slightly a bit less crazy even. Neural networks are just a mathematical expression. They take the input data as an input, and they take the weights of a neural network as an input. And it's a mathematical expression, and the output are your predictions of your neural net or the loss function. We'll see this in a bit. But basically, neural networks just happen to be a certain class of mathematical expressions. But backpropagation is actually significantly more general. It doesn't actually care about neural networks at all. It only cares about arbitrary mathematical expressions. And then we happen to use that machinery for training of neural networks. Now, one more note I would like to make at this stage is that, as you see here, micrograd is a scalar-valued autograd engine. So it's working on the level of individual scalars, like -4 and 2. And we're taking neural nets and we're breaking them down all the way to these atoms of individual scalars and all the little pluses and times, and it's just excessive. And so obviously you would never be doing any of this in production. It's really just put down for pedagogical reasons because it allows us to not have to deal with these n-dimensional tensors that you would use in modeling deep neural network library. So this is really done so that you understand and we factor out backpropagation and chain rule and understanding of neural network training. And then if you actually want to train bigger networks, you have to be using these tensors, but none of the math changes. This is done purely for efficiency. We are basically taking all the scalar values, we're packaging them up into tensors, which are just arrays of these scalars. And then because we have these large arrays, we're making operations of those large arrays that allows us to take advantage of the parallelism in a computer. And all those operations can be done in parallel, and then the whole thing runs faster. But really none of the math changes, and they're done purely for efficiency. So I don't think that it's pedagogically useful to be dealing with tensors from scratch. And that's why I fundamentally wrote micrograd, because you can understand how things work at the fundamental level, and then you can speed it up later. Okay, so here's the fun part. My claim is that micrograd is what you need to train neural networks, and everything else is just efficiency. So you'd think that micrograd would be a very complex piece of code, and that turns out to not be the case. So if we just go to micrograd, and you'll see that there's only 2 files here in micrograd. This is the actual engine. It doesn't know anything about neural nets, and this is the entire neural nets library on top of micrograd. So engine and nn.py. So the actual backpropagation autograd engine that gives you the power of neural networks is literally 100 lines of code of like very simple Python, which we'll understand by the end of this lecture. And then nn.py, this neural network library built on top of the autograd engine, is like a joke. It's like we have to define what is a neuron, and then we have to define what is a layer of neurons, and then we define what is a multi-layer perceptron, which is just a sequence of layers of neurons. And so it's just a total joke. So basically, there's a lot of power that comes from only 150 lines of code, and that's all you need to understand neural network training, and everything else is just efficiency. And of course, there's a lot to efficiency, but fundamentally that's all that's happening. Okay, so now let's dive right in and implement micrograd step by step. The first thing I'd like to do is I'd like to make sure that you have a very good understanding intuitively of what a derivative is and exactly what information it gives you. So let's start with some basic imports that I copy-paste in every Jupyter notebook always. And let's define a function, a scalar valued function, f of x, as follows. So I just made this up randomly. I just wanted a scalar valued function that takes a single scalar x and returns a single scalar y. And we can call this function, of course, so we can pass in, say, 3.0 and get 20. Back. Now,
Oops.
We can also plot this function to get a sense of its shape. You can tell from the mathematical expression that this is probably a parabola, it's quadratic. And so if we just create a set of scale values that we can feed in, using, for example, a range from -5 to 5 in steps of 0.25. So x is just from -5 to 5, not including 5, in steps of 0.25. And we can actually call this function on this numpy array as well. So we get a set of y's if we call f on x's. And these y's are basically also applying the function on every one of these elements independently. And we can 5 to 5 in steps of 0.25. Mathematical expression that this is probably a parabola, it's quadratic. And so if we just create a set of scalar values that so x is just from -5 to 5, not including 5, in steps of 0.25. And we can actually call this function on this numpy array as well. So we get a set of y's if we call f on x's. And these y's are basically also applying the function on every one of these elements independently. And we can plot this using matplotlib. So plt.plot x's and y's, and we get a nice parabola. So previously here, we fed in 3.0 somewhere here, and we received 20 back, which is here, the y coordinate. So now I'd like to think through what is the derivative of this function at any single input point x, right? So what is the derivative at different points x of this function? Now, if you remember back to your calculus class, you've probably derived derivatives. So we take this mathematical expression, 3x squared minus 4x plus 5, and you would write out on a piece of paper and you would apply the product rule and all the other rules and derive the mathematical expression of the great derivative of the original function. And then you could plug in different x's and see what the derivative is. We're not going to actually do that because no one in neural networks actually writes out the expression for the neural net. It would be a massive expression. It would be thousands, tens of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just make sure that we really understand what the derivative is measuring, what it's telling you about the function. And so if we just look up derivative, we see that, okay, so this is not a very good definition of derivative. This is a definition of what it means to be differentiable. But if you remember from your calculus, it is the limit as h goes to 0 of f of x plus h minus f of x over h. So basically what it's saying is if you slightly bump up you're at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by a small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down, and by how much? And that's the slope of that function, the slope of that response at that point. And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.001. And let's say we're interested in point 3.0. So we can look at f of x, of course, is 20. And now f of x plus h. We're just going to pick a very small h, 0.001. And let's say we're interested in point 3.0. So we can look at f of x, of course, is 20. And now f of x plus h. So if we slightly nudge x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20? Or do you expect it to be slightly lower than 20? And since this 3 is here, and this is 20, if we slightly go positively, the function will respond positively. So you'd expect this to be slightly greater than 20. And now by how much is telling you the strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the function responded.
in the positive direction, and we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope, because we have to make h very, very small to converge to the exact amount, because expect x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20, or do you expect it to be slightly lower than 20? And since this 3 is here, and this is 20, if
okay, so that's 6x plus, so 6x minus 4. So that's 6 times 3. That's 18. 18 minus, so it's 14. Yeah.
we slightly go positively, the function will respond positively. So you'd expect this to be slightly greater than 20. And by how much is telling you the sort of the strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the function responded in the positive direction. And we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope, because we have to make h very, very small to converge to the exact amount. Now, if I'm doing too many zeros, at some point, I'm going to get an incorrect answer, because we're using floating point arithmetic, and the representations of all these numbers in computer memory is finite, and at some point we get into trouble. So we can converge towards the right answer with this approach. But basically, at 3, the slope is 14. And you can see that by taking 3x squared minus 4x plus 5 and differentiating it in our head. So 3x squared would be 6x minus 4. And then we plug in x equals 3. So that's 18 minus 4 is 14. So this is correct. So that's at 3. Now, how about the slope at, say, negative 3? What would you expect for the slope? Now, telling the exact value is really hard, but what is the sign of that slope? So at negative 3, if we slightly go in the positive direction at x, the function would actually go down. And so that tells you that the slope would be negative. So we'll get a slight number below 20. And so if we take the slope, we expect something negative 22. Okay. And at some point here, of course, the slope would be 0. Now, for this specific function, I looked it up previously, and it's at point 2 over 3. So at roughly 2 over 3, that's somewhere here, this derivative would be 0. So basically, at that precise point, if we nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case. So we're going to start, complexifying a bit. So now we have a function here with output variable d that is a function of 3 scalar inputs, a, b, and c. So a, b, and c are some specific values, 3 inputs into our expression graph, and a single output d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to, again, look at the derivatives of d with respect to a, b, and c. And think through, again, just the intuition of what this derivative is telling us. So in order to evaluate this derivative, we're going to get a bit hacky here. We're going to, again, have a very small value of h. And then we're going to fix the inputs at some values that we're interested in. So this is the point ABC at which we're going to be evaluating the derivative of d. This is the input d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to, again, look at the derivatives of d with respect to a, b, and c. And think through, again, just the intuition of what this derivative is telling us. So in order to evaluate this derivative, we're going to get a bit hacky here. We're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this is the point ABC at which we're going to be evaluating the derivative of d with respect to all a, b, and c at that point. So there's the inputs, and now we have d1 is that expression. And then we're going to, for example, look at the derivative of d with respect to a. So we'll take a and we'll bump it by h. We're going to get a bit hacky here. We're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this is the point ABC at which we're going to be evaluating the derivative of d with respect to all a, b, and c at that point. So there's the inputs, and now we have d1 is that expression. And then we're going to, for example, look at the derivative of d with respect to a. So we'll take a and we'll bump it by h, and then we'll get d2 to be the exact same function. And now we're going to print
Oops. Weird.
f1, d1 is d1, d2 is d2, and print slope. So the derivative or slope here will be, of course, d2 minus d1 divided h. So d2 minus d1 is how much the function increased when we bumped the specific input that we're interested in by a tiny amount. And this is then normalized by h to get the slope. So yeah, so if I just run this, we're going to print d1, which we know is 4. Now d2 will be bumped, a will be bumped by h. So let's just think through a little bit what d2 will be printed out here. In particular, d1 will be 4. Will d2 be a number slightly greater than 4 or slightly lower than 4? And it's going to tell us the sign of the derivative. So we're bumping a by h. So 4. And it's going to tell us the sign particular what D2 will be printed out here. In particular, D1 will be 4. Will D2 be a number slightly greater than 4 or slightly lower than 4? And it's going to tell us the
Wait, okay, so the okay. So A is going to be lower because you're multiplying by negative. Okay, cool.
the sign of the derivative. So we're bumping A by H. B is -3, C is 10. So you can just intuitively think through this derivative and what it's doing. A will be slightly more positive, but B is a negative number. So if A is slightly more positive, because B is -3, we're actually going to be adding less to D. So you'd actually expect that the value of the function will go down. So let's just see this. Yep, and so we went from 4 to 3.9996. And that tells you that the slope will be negative. And
So why is that derivative not changing? So okay. So that becomes wait. Counting out somewhere? Oh right. So the actual calculation happening is 2 times -3 plus 10 minus 2 minus 0.01 divided by minus 0.1. Okay, so that's the actual calculation happening. So then this is a smaller number now, so the negative is going to be smaller. So a smaller negative, like we can remove the plus 10, that's just like taking into space. So that's going to be smaller, and then that's going to get divided by then what we had. Plus. Okay. Now the negative is larger. So it's going to be -6 minus like 6 minus 6 point like thing. Probably like -6 or something, or like -5 or something. I think it's -5 or something. Yeah. So minus the minus, so plus. So it becomes 6 minus okay. So that's minus 6 minus that. So then that's like 1. And then that becomes a. Oh shit. Okay, it's literally the same thing. Okay, so it's literally the same thing. So why is it the same thing? So because we have A times B plus C minus A plus H plus C. Wait. So whatever signs positive and negative, so negative, so positive times. Wait, so that's a weaker. So then that's a less positive. Okay. So because we're multiplying by a negative, so it's going to be plus 2 minus. Oh, So ale wpiskujesz do przyczyny, że to jest powiedz inaczej. Okay. So 8 plus. So that's a positive plus around. Okay, so great positive. Great positive. Means that. Super. So sometimes it's more, sometimes it's less. Okay. Great. Yeah, so mhm. So normally it'd be the same. Sometimes we add a little bit, make it more negative. And then there's a little bit extra we share off. Sometimes maybe then there's a holy shit. Wait, what? Okay, so the amount, like I said, the amount is literally going to be the same. Um, wait, okay, so okay. Yeah, so then when you do a minus, that's the bottom one, which ends up. So that becomes plus 6. So when there's less positive, then there's more on the negative, so then there's that gets passed along. And so then it's negative divided by 0.01. And then there's the positive. Wait, so when it's a negative, right? Oh, wait. So that's not a, okay. So, oh shit, okay. What? Wait. Hmm? the hell? That should be 6 minus. Mhm. Oh, wait. Nope. Mm. Yeah, no. It's all the same. Um. Oh. Okay. Mhm. Wait. Okay. So wait. It is changing. Hold on a second. What the fuck? Right. Now. So what's going on here? Why is it not changing here? Oh, right. Okay. Okay. Hmm. Yeah, so it's more positive. But yeah, of course, it's a negative. So, mm,
And then
no. Wait, hold on a second. That. Down a bit. Oh. Wait, that's true. Okay. No, positive. Yeah, positive. That's right. Mm. Okay, so it's getting the. That's right. Okay. Now that is the strange one. Oh, oh, it's because I'm doing the other way around. Ah, oh, okay, now it's all making sense. Okay. Ah, okay. So now I'm doing the life. So, oh, so if it's a bit more negative, then hmm, better negative number gets through, better negative number gets through. Positive, 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 positive. Mm, mm. Okay.
Will be a negative number because we went down, and then the exact
No.
number of slope will be exact amount of slope is -3. And you can also convince yourself that -3 is the right answer mathematically and analytically, because if you have a times b plus c, and and you have calculus, then differentiating a times b plus c with respect to a gives you just b. And indeed, the value of b is -3, which is the derivative that we have. So you can tell that that's correct. So now if we do this with b, so if we bump b by a little bit in a positive direction, we'd get different slopes. So what is the influence of b on the output d? So if we bump b by a tiny amount in a positive direction, then because a is positive, we'll be adding more to d, right? So and now what is the sensitivity? What is the slope of that addition? And it might not surprise you that this should be 2. And why is it 2? Because d of d by db, differentiating with respect to b, would give us a. d by db, differentiating with respect to b, would give us a. And the value of a is 2. So that's also working well. And then if c gets bumped at d by db, differentiating with respect to b, would give us a. And the value of a is 2. So that's also working well. And then if c gets bumped a tiny amount in h by h, then of course a times b is unaffected, bumped a tiny amount, and the value of a is 2. So that's also working well. And then if c gets bumped a tiny amount in h by h, then of course a times b is unaffected. And now c becomes slightly bit higher. What does that do to the function? It makes it slightly bit higher because we're simply adding c. And it makes it slightly bit higher by the exact same amount that we added to c. And so that tells you that the slope is 1. That will be the rate at which d will increase as we scale c. Okay, so we now have some intuitive sense of what this derivative is telling you about the function, and we'd like to move to neural networks. Now, as I mentioned, neural networks will be pretty massive expressions, mathematical expressions. So we need some data structures that maintain these expressions, and that's what we're going to start to build out now. So we're going to build out this value object that I showed you in the README page of micrograd. So let me copy paste a skeleton of the first very simple value object.
What?
So
Returned string of the mm.
So class value takes a single scalar value that it wraps and keeps track of, and that's it. So we can, for example, do value of 2.0, and then we can look at its content. And Python will internally use the wrapper function to return this string. Oops, like that. So this is a value object with data equals 2 that we're creating here. Now what we'd like to do is we'd like to be able to have not just like
Wait, what? Why does it say that? Ah. Okay.
Now what we'd like to do is we'd like to be able to have not just like two values, but we'd like to do A plus B, right? We'd like to add them. So currently you would get an error because Python doesn't know how to add two value objects. So we have to tell it. So here's addition. So you have to basically use these special double underscore methods in Python to define these operators for these objects. So if we call if we use this plus operator, Python will internally call a dot add of b. That's what will happen internally. And so b will be the other, and self will be a. And so we see that what we're going to return is a new value object, and it's just it's going to be wrapping the plus of their data. But remember now, because data is the actual like numbered Python number, so this operator here is just the typical floating point plus addition now. It's not an addition of value objects. And we'll return a new value. So now a plus b should work, and it should print value of -1, because that's 2 plus minus 3. There we go. Okay, let's now implement multiply, just so we can recreate this expression here. So multiply, I think it won't surprise you, will be fairly similar. So instead of add, we're going to be using mul, and then here, of course, we want to do times. And so now we can create a C value object, which will be 10.0. And now we should be able to do A times B. Well, let's just do A times B first. That's value of -6 now. And by the way, I skipped over this a little bit. Suppose that I didn't have the repr function here. Then it's just that you'll get some kind of an ugly expression. So what wrapper is doing is it's providing us a way to print out like a nicer looking expression in Python. So we don't just have something cryptic. We actually are, it's value of -6. So this gives us a times, and then this we should now be able to add C to it because we've defined and told the Python how to do mul. And add. And so this will basically be equivalent to a dot mul of b, and then this new value object will be dot add of c. And so let's see if that worked. Yep, so that worked well. That gave us 4, which is what we expect from bit 4. And I believe we can just call them manually as well. There we go. So, yeah. Okay, so now what we are missing is the connected tissue of this expression. As I mentioned, we want to keep these expression graphs. So we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children. And by default, it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call _prev, which will be the set of children. This is how I did it in the original micrograd, looking at my code here. I can't remember exactly the reason. I believe it was efficiency, but this _children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a so now when we are creating a value in us, which we'll call, there will be an empty tuple. Example, we are going to about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children, and by default, it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call _prev, which will be the set of children. This is how I did it in the original micrograd, looking at my code here. I can't remember exactly the reason. I believe it was efficiency, but this _children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now, when we are creating a value like this with a constructor, children will be empty and prep will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. So those are the value, which in this case is self, and prep will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. The efficiency, underscore prime, which will be the set of the children. This is how I did it in the original micrograd, looking at my code here. I can't remember exactly the reason. I believe it was efficiency, but this underscore children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set. I believe for efficiency. So now, when we are creating a value like this with a constructor, children will be empty and prep will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. So those are the children here. So now we can do d dot prep, and we'll see that the children of the, we now know, are this a value of -6 and value of 10. And this, of course, is the value resulting from a times b and the c value, which is 10. Now, the last piece of information we We don't know. So we know now the children of every single value, but we don't know what operation created this value. So we need one more element here. Let's call it underscore pop. And by default, this the children of the we now know the data as well, which is because we've defined and told the Python how to do mul and add. And so this will basically be equivalent to a dot mul of b, and then this new value object will be dot add of c. And so let's see if that worked. Yep, so that worked well. That gave us 4, which is what we expect from before. And I believe we can just call the manually. As well. There we go. So, yeah. Okay, so now what we are missing is the connective tissue of this expression. And I believe we can just call them manually as well. There we go. So, as I mentioned, we want to keep these expression graphs. So we need to know and keep pointers about what values produce what other values. So here, for example, we are going to introduce a new variable, which we'll call children. And by default, it will be an empty tuple. And then we're actually going to keep a slightly different variable in the class, which we'll call underscore prev, which will be the set of children. This is how I did it in the original micrograd, looking at my code here. I can't remember exactly the reason. I believe it was efficiency, but this underscore children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set, I believe for efficiency. So now when we are creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children. Creating a value like this with a constructor, children will be empty and prev will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. So those are the children here.
दाई नाम की लड़की है जो कभी कभार मैथ्स लेती है इंग्लिश लेती है उसको मैं कॉन्ट्रैक्ट है वो भी अभी वो भावना के साथ कर रही है लेक्चर इंग्लिश जिन सबको दे रहे हैं वही देना चाहिए लेकिन कभी कभार मैथ्स और इंग्लिश करती है ना लाइक अभी हाफ लाइक 2 3 सेशन इंग्लिश हो गए 2 3 सेशन मैथ्स ऐसा नहीं चलेगा तो जो करना है वही करना तो पेपर भेजो भावना को हैंडल करो सबको एक ही पेपर दे दो टीचर को बोलो टीचर के डिसाइड
So now we can do d dot prep, and we'll see that the children of the, so those are the children here.
Oh, hi. Hello? Okay. I just let you know I'm going to be playing like the tutorial and stuff whilst doing that. So, sorry if the noise is loud. Let me know if you want me to turn it down.
I'm looking at my code here. I can't remember exactly the reason. I believe it was efficiency. But this underscore children will be a tuple for convenience, but then when we actually maintain it in the class, it will be just this set. I believe for efficiency. So now, when we are creating a value like this with a constructor, children will be empty. It will be just this set. I believe for efficiency. So now, when we are creating a value like this with a constructor, children will be empty and prep will be the empty set. But when we're creating a value through addition or multiplication, we're going to feed in the children of this value, which in this case is self and other. So those are the children here. So now we can do beat out, right? And we'll see that the children of the, we now know see that the children of the we now know are this value.
Okay, so there is no such thing. Okay. So self-taught prep equals set by children. Okay, children. Okay. Okay, so that did not work. So why did that not work? So right.
normally if it's like a yeah, doesn't just on a paper. भावना और रकम भी नहीं उनको normally है
Wait. Oh wait, okay, so children is a defined thing. Children is a defined thing. Okay, yes. Um what? That's invalid syntax. Why is that invalid syntax? Oh, so that does work. Okay. No, it does have it. I can see it because I made it. Okay, and ran. Yes, it does. It has that attribute. Why is this not working? What is wrong? What is the problem? God damn. Okay, so still saying Oh, I am dumb. Yes, yes. Okay, so this is all just. So all we're doing is saying that this thing equals.
Joining us at the gallery tonight is a young man who truly loves our police. His name is DJ Daniel. He is 13 years old, and he has always dreamed of becoming a police officer. But in 2018, DJ was diagnosed with brain cancer. The doctors gave him 5 months at most to live. That was more than 6 years ago.
For most of the past few years, America's economy has been the envy of the developed world. The US has enjoyed better GDP, productivity, and wage growth than basically every peer economy. And last year, inflation came down from its lofty highs, falling to a low of 2.4% year on year in September. However, all of a sudden, the American economy has started to look a bit shaky. Consumer confidence has apparently plummeted, the trade deficit is widening, and inflation is looking dangerously sticky. While we won't get the official data for a couple of weeks, the latest GDP Now forecast, a real-time estimate of GDP maintained by the Federal Reserve Bank of Atlanta, suggests that year-on-year US GDP is on track to shrink by an astonishing 2.8% in the first quarter. So in this video, we're going to explain how and why the US economy has started to look a bit shaky, and how much of it has to do with Trump. Do you have questions about TLDR's bias? Watch us respond to your criticisms in a dedicated criticism response video. It's linked in the description. So let's just get straight into it. Explain why the Atlanta Fed thinks that the US is on the brink of a recession, if not in one already.
Gay or depressed? It's a hard choice. It's a hard choice. Let me show it to you. Yeah, just throw it up there one more time. Gay or depression? Yeah, the problem is I excel at both of these. Yeah. That's what I was saying. Yeah. Let me see gay one more time just in case. Gay or depression? It's a hard choice. It's a hard choice. Let me show it to you. Yeah, just throw it up there one more time. Gay or depression? Yeah, the problem is I excel at both of these. Yeah. That's what I was saying. Yeah. Let me see gay one more time just in case. Gay or depression? It's a hard choice. It's a hard choice. Let me show it to you. Yeah, just throw it up there one more time. Gay or depression? Yeah, the problem is I excel at both of these. Yeah. That's what I was saying. Yeah. Let me see. First of all, this dude got 8 baby mamas. Damn, kids all hate your guts and bank account don't got no commas. You a monster face could win a Frankenstein lookalike contest. Scared the doctors on the day you was born. I wish that they dropped you so we wouldn't have to deal with your bullshit. My problem with you is your entire existence. I wish that your parents hadn't met. Wish your body would be eaten by your pet and at your funeral when your loved ones never wept. You a bum ass bitch. I hate your face, body, brain, and your dumb ass bitch. You undeserving of love. You should call life quits. Genuinely, I think we're better off if you don't exist. And when you walk in a room, everyone gets pissed. Someone called Dr. Allen Luce because you smell like shit. Sorry, can I tell you why I hate the dumb hoe real quick? He got the nerve to show his ugly face around my clit. And yeah, it makes me sick. And yeah, I cut the beat off so you can hear me. So put me on speaker. I got a message for your family. Yo mama's ugly. Yo dad is bumming. The genes that you're sharing should be erased. It's the disgusting. Disintegrate them all, make sure they never come again. Like everyone you sleep with, they be disappointed. And yeah, I'm judgmental because I think it's mental that everybody here acts like this fool is some kind of genius. He's a tool, he's a poser, he's a liar, and I hope that and one day y'all gonna see why my hate justified, motherfucker. And that seems like it's a bit extreme. However, I do feel this way about many people, so I see where they're coming from. First of all, this dude got 8 baby mamas. Damn, kids don't hate your guts and bank account don't got no commas. You a monster, face could win a Frankenstein lookalike contest. Scared the doctors on the day you was born. I wish that they dropped you so we wouldn't have to deal with your bullshit. My problem with you is your entire existence. I wish that your parents hadn't met. Wish your body would be eaten by your pet and at your funeral your loved ones never wept. You a bum ass bitch. I hate your face, body, brain, and your dumb ass fit. You undeserving of love. You should call life quits. Genuinely, I think we're better off if you don't exist. And when you walk in a room, everyone gets pissed. Someone called Dr. Alley Loops because you smell like shit. Sorry, and can I tell you why? I hate the dumb hoe real quick. You got the nerve to show his ugly face around my clip. And yeah, it makes me sick. And yeah, I cut the beat off so you can hear me. So put me on speaker. I got a message for your family. Yo mama's ugly. Yo daddy's bumming. The G's that you're sharing should be erased. It's disgusting. Disintegrate them all. Make sure they never come again. Like everyone you sleep with, they be disappointed. And yeah, I'm judgmental. Because I think it's mental that everybody here acts like this fool is some kind of genius. He's a tool. He's a poser. He's a liar. And I hope that and one day y'all gonna see why my hate justified, motherfucker. And that seems like it's a bit extreme. However, I do feel this way about many people, so I see where they're coming from. First of all, this dude got 8 baby mamas. Damn, kids don't hate your guts and bank account don't got no promise. You a monster, face could win a Frankenstein lookalike contest. Scared the doctors on the day you was born. I wish that they dropped you so we wouldn't have to deal with your bullshit. My problem with you is your entire existence. I wish that your parents hadn't met. Wish your body would be eaten by your pet and at your funeral your loved ones never wept. You a bum ass bitch. I hate your face, body, brain, and your dumb ass fit. You undeserving of love. You should call life quits. Genuinely, I think we're better off if you don't exist. And when you walk in a room, everyone gets pissed. Someone called Dr. Alley Loops because you smell like shit. Sorry, man, can I tell you why I hate the dumb hoe real quick? You got the nerve to show his ugly face around my clip. And yeah, it makes me sick. And yeah, I cut the beat off so you can hear me. So put me on speaker. I got a message for your family. Yo mama's ugly. Yo daddy's bumming. The G's that you're sharing should be erased. It's disgusting. Disintegrate them all. Make sure they never come again. Like everyone you sleep with, they be disappointed. And yeah, I'm judgmental because I think it's mental that everybody here acts like this fool is some kind of genius. He's a tool. He's a poser. He's a liar. And I hope that and one day y'all gonna see why my hate justified, motherfucker. And that seems like it's a bit extreme. However, I do feel this way about many people, so I see where they're coming from. First of all, this dude got 8 baby mamas. Damn, kids don't hate your guts and bank account don't got no promise. You a monster, face could win a Frankenstein lookalike contest. Scared the doctors on the day you was born. I wish that they dropped you so we wouldn't have to deal with your bullshit. My problem with
Smell is a sense that evokes very strong emotional and bodily reactions, and in particular, it speaks very strongly to disgust, such as the so-called feta judaicus, which is the smell of Jews that Hitler talked about in Mein Kampf. During the transatlantic slave trade, this technique was used to uncover black bodies and to actually legitimize racism. There were comments that were straightforwardly misogynistic and things saying that women shouldn't be in academia, they should be having babies, and looking after their husbands. They were considering it woke nonsense, essentially.
The severity of online trolling is something that Cambridge College is becoming more and more now.
I've seen examples of misogyny online accounts also measured on career static. So it's not a new phenomenon, but it's really a strange one in this case. I think people will pick on a very sensible academic subject and a proud post from somebody who's just made a great achievement and is just treated as some sort of culture war, which shows that it is this point.
That particular social media platform has become so negative, so it became, so I think for that reason, Ali has shown lots of people, myself included, how you can do things differently, how you can be kind and recognize other people's humanities. And I think about very often, despite working on negative smells the vast majority of the time. Hi, I'm Dr. Ali Roots, and I'm a supervisor in English literature here at the University of Cambridge. My PhD thesis, titled Olfactory Ethics, the Politics of Smell in Modern Contemporary Prose, recently went viral online. I posted a photograph of myself holding this I think about very often. Despite work.
What is this? I don't understand. What?
Can you go ahead and make a new AWS S3 bucket for me? Give it a random name so that we don't hit a collision with another bucket. Thank you. All right, Claude's going to ask to use a tool or use model context protocol. And Claude just made me an AWS S3 bucket called Claude Storage Bucket. Let's see if there's anything inside it. I'll refresh the interface here. General purpose. Look at that, Claude Storage Bucket. This may or may not be the future. Who knows? But I am using this thing, MCP server AWS. You feed it AWS keys, and it can do stuff. It'd be pretty cool if we could upload an object. We give it a try. We try more. Great, thanks for doing that, Claude. Can you place a new object in the bucket? You can maybe write a poem and call it poem.text or poem.txt. Upload it to the bucket for me. Thanks. Let's see what we get here. All right, poem key, file content. Doesn't really look like a poem, but maybe it's base 64. Running upload. Allow. I don't know why I had to hit allow twice. Written a poem called Hidden Paths. Here's the. I don't want to see the content. I want to download it. Refresh over here. Look at that poem.txt. All right. Let's see what Claude wrote for us. Hidden Paths. Beneath the canopy of time. Light shadow over time. Very nice. Very nice. All right. That is the model context protocol. Kind of good usage. This is my first time ever using model context protocol, but this is MCP server AWS. I don't know. What do you guys think? Are we going to be configuring infrastructure via Claude prompts in the future? And then what if you hook your cursor up? Dear Claude, please write my app and deploy to prod. Go. Kind of interesting.
मैं तो बहुत जल्दी से कुछ चेंज करके आऊँ ओके ओके हाँ जी लॉगिन आईडी शुरू करना है सानवी जाओ जल्दी से क्या चीज हाँ हम प्लानिंग करेंगे ठीक है पहले देखते हैं कितना टाइम बचा है कोई बात नहीं जाओ जाओ चेंज करो जल्दी चेंज करके आओ आ जाओ और उसको बोलो कि व्हाट यू पे for सामान and you can send me मर्चा मैंने भेजा था उसमें से क्यों नहीं भेजा मैंने क्योंकि मुझे वो बाकी नैतिक और वो बीच गया नैतिक वाला हाँ ना वो एक रह गया आई गेस उन्होंने ऑलरेडी किया है कल पेपर आए थे लोग मुझे तो एक और मैंने भेजा है नैतिक वाला ना दो बेटा आज लेट हो जाएगा Chinese company or that region as well, it's really necessary. We do not have anything on that. But if there is such case that we require something, and if we one or something, we can arrange that as well. In that instead of what is the mock test are being going on, let me make sure that we mock test. Starting from 17th of May. Yes. So they have now two people that they are arranging. Working status, PSC, PSSE, and JLA. So you can need to try lessons and see how it goes, and then after we need to get more information. So we're talking about time lessons. We have a batch for site going on Sunday. The timing are 4 to 16, 4 to 5 is for English, and 5 to 6 would be for maths. Is that okay for you? We have one more batch on Tuesday as well. The timing are 5 to 7. Like one of the maths, one of the English. Tuesday as well, and Sunday I don't have what time. What other things are to do? We have two batches on Sunday, one on Tuesday. So if you want one-on-one lesson, we can arrange that. Next, Sunday, the other time, we have on Sunday, 5 to 7 and 4 to 6. What time is it? And then they give me a message or something, and then the details in the WhatsApp itself. You let me know the deal of money and we will arrange the one-on-one lesson to master before the subject according to the guidelines. Maybe this is what topics you need to cover on one-on-one lessons for the child, like for math, we will engineer something like an something, and this we will discuss on the lesson the same for the teacher.
चांदी है यहाँ पे पेपर रखा है, देख भी जाना। एक और पेपर नहीं, एक अच्छा हाँ और श्री का हाँ ठीक। बच्चों को जहाँ राइटिंग करना है ना शांति, देखो कंप्रीहेंशन में जहाँ राइटिंग करना है उसमें जगह नहीं है तो पहले से ही उनको लाइन पेपर दे देना। यहाँ से लाइन पेपर एक नोटबुक लेके जाओ, है ना? हाँ तो सबको लाइन पेपर देते रहना, उस पर लिखने नहीं दो। हाँ और एक बार सबको रिमाइंड कर देना, दे हैव टू फॉलो द स्पैन। सानवी बेटा चलो तैयार हो जाओ नानू जाओ जो जैकेट पहन के चलो उसको सेंड कर दो टेक्स्ट अगर तुम नहीं आओगी तब पर भी चार्ज किया जाएगा हाँ क्योंकि ऐसे टाइम पास के लिए लोग नहीं आए and make the payment for this month आगे बात बेटा नानी ऊपर जाके बैठो ना बेटा नानो ऊपर जाके बैठो नहीं आओ आओ मेरा भी जैकेट लेके आओ आपने मुझे दिया नहीं तो हमें दिला दिया
Please, Meena from Currently. Sorry, I haven't got a chance to meet you. So are you coming today? Yeah. Okay, did you brother send you something for the office? No, did he tell you regarding talented women project? He hasn't explained you what to do. Okay, so when you go to the academy, you give a call to your brother. He should be able to explain you what you have to do. Yeah, and if any confusion, give me a call. Okay? Yeah, please. ऑनलाइन पे किया ना ये क्लास दिन उसमें बोला देखिए 40 गुण देखे थे बुक का अभी 40 डेज के बाद ही उसमें ऑनलाइन पे किया और रजिस्ट्रेशन पे किया मैं ऐसे लोगों को भी देखने वाला हूँ बिल्कुल लास्ट वो आया उसमें तो मुझे चांदनी आओ नीचे जाना है कि नहीं बेटा हाँ तो तुम नहीं जाके ऊपर बैठो ना स्केटिंग का लेके आना अपना फिर वहाँ पहुँच चुकी है तुम वहाँ बैठ सकते हैं Random, out please.
सानवी नहीं होएगा हाँ क्या चीज क्या अब तो हम लाइब्रेरी नहीं जा पाएंगे इट्स टू लेट इट्स जस्ट टू लेट मैं कब से चिल्ला रही तुम नहीं आ रहे नहीं अभी हम टाइम से वहां ही पहुंचे है कभी इसका साथ ही था ना तुम जूता पहना यार तुम्हें तो 2 दिन तक नहीं यस ये पकड़ इसने मुझे कर दिया ठीक है फिर मैं फोन ले ही ले रही हूँ हाँ मैं 10 मिनट निकल ले रही हूँ ठीक है तो ये मैं तुम्हें भेजती हूँ क्या करना है चलो शांति में जा रही हूँ अरे लाडू चाबी कहाँ गई मैंने कौन सा लॉक किया है अच्छा ठीक है चलो अच्छी बात है